Okay guys, here is a full kinetics kinds of a question. Could show up on an exam. This is everything all smashed together, all the way from orders of the reaction up through plausible mechanisms. So we're going to look at the reaction of methyl iodide, that's that CH3I, and its reaction with bromide ion to form bromomethane or methyl bromide, and iodide ion. The following kinetics data was taken. What is the generic rate law? Remember, the generic rate law is the rate is equal to K. And for this particular reaction, we're going to look at what the order is with respect to the methyl iodide and what the order is with respect to the bromide. We have to get that from the kinetics data. We're looking for N and M when we're talking about a generic rate law. What is the value in the units for the rate constant? That's the rate constant right there is K. After we get the orders of the reaction, we can plug things in to figure out what the rate constant is. And then from there we can go on to the concentration after a certain amount of time. That's the integrated rate laws because time is involved. You can't jump to the integrated rate laws until you know what the order of the reaction is, because they're different for each order of the reaction, for the different orders. And then finally, the proposed mechanism. Is it plausible? And this is a tough one. When you have the fast first equilibrium step, the kinetics to figure out if it's a plausible mechanism are tough. So let's get started and go right in to figuring out the generic rate law. So, for the reaction of methyl iodide with bromide, here's the data. The generic rate law. This is where you take the ratio of the rates equals the ratio of the concentration raised to the order. We have two different reactants here, so we have to take each one individually. So the first thing we're going to do is the order of the reaction with respect to the methyl iodide. Looking at the rate data, we're going to use experiment 1 and experiment 2 because in those experiments the bromide ion is constant concentration. So that means any change in the rate is due exclusively to the methyl iodide. So, with regard to the methyl iodide, the ratio of the rates, 1.93, divided by 0.552, is equal to the ratio of the concentration, 1.96 over 0.56, raised to the order. If you do the math on that, what you end up getting is 3.5 is equal to 3.5 to the order. With respect to the methyl iodide, the reaction is first order. Because 3.5 to the first power is 3.5, so the order is equal to 1. Now, we have to figure out the ratio of the order of the reaction with respect to the bromide ion. For the bromide ion, we're going to take experiment 1 and compare it to experiment 3 because the methyl iodide concentration is being held constant. So any change in the rate is coming from the bromide ion. So once again, the ratio of the rates, 1.49 divided by 0.552 is equal to 1.51 divided by 0.56 to the order. So if you do the math on that, you get 2.7 is equal to 2.7 to the order. So once again, that means that with respect to the bromide ion, it is also a first order reaction because anything to the first power is itself, so the order is equal to 1. So the generic rate law for this reaction, rate is equal to the rate constant times the concentration of methyl iodide to the first power times the concentration of bromide ion to the first power. Now that we have the rate law, the generic rate law, we can continue on. What is the value in units for the rate constant? This is an overall second order reaction. We take the fact that it's to the first power for the methyl iodide, the fact that it's the first power for the bromide, we add them together to get the second order reaction. So our units for our rate constant should match up for the second order. So what we're going to do now is take the rate, and I'm just using experiment 1. You can use any of those experiments that you want to. The rate on experiment 1 was 0.552 moles per liter second is equal to the rate constant times the concentration, and again the concentration in experiment 1 was 0.56 moles per liter for the methyl iodide, and it was 0.56 moles per liter for the bromide ion. So now we're going to do some math. This is just math at this point. I'm going to leave the left-hand side of my equation the same. 0.552 moles per liter second is equal to K times 0.56 times 0.56 gives me 3136, I'm sorry. And the units are going to be moles squared per liters squared. Moles times moles on the top, liters times liters on the bottom. Now we're going to take and multiply by liters squared over 0.3136 moles squared. What you do to the left-hand side has to be what you do to the right-hand side. That means that my liters squared cancels with my liters squared. Mole squared cancels with mole squared. 0.3136 cancels with 0.3136. We get K. Over on my other side, one of the liters cancels with one of the liters. One of the moles cancels with moles. Now we got to do the math. 0.552 divided by 0.3136 gives you 1.76. And the units, liters per mole second, which matches up for a second order overall reaction. So this is the value and the correct units for my rate constant. So now we want the concentration of the methyl iodide after a minute, the concentration of the bromide after a minute. Whenever you're looking for a concentration at a particular time, that is the symbol to you, or the way that you should recognize that you now need the integrated rate laws. Because in the integrated rate laws, you have concentration at various times. So the integrated rate law for a second order overall reaction is 1 over the concentration at time t is equal to the rate constant times time plus 1 over the concentration of the initial. We just have to sort of plug things in at this point. So what is the concentration of methyl iodide after 1 minute? So we've got to be careful. My rate constant is in terms of a second. So we have to make sure that these units match up. So 1 minute is equal to 60 seconds. So we want the concentration of the methyl iodide at 60 seconds is equal to the rate constant, 1.76 liters per mole second, times 60 seconds, plus 1 over the initial concentration. 1 over the concentration of methyl iodide at 60 seconds. Hold on, that My tablet kind of messed up there. Is equal to 1.76 times 60 is 105.6. Seconds cancels with seconds. Liters per mole. Plus 1 over a molar is 1 over moles per liter, which inverts it, 1 liters per mole. So we keep going. 1 over the concentration of methyl iodide at 60 seconds is equal to 106.6 liters per mole. Take the inverse of both sides, or multiply both sides by the concentration of methyl iodide, and then take 1 divided by 106.6. Both of them will get you to the same place, that the concentration of methyl iodide at 60 seconds is equal to 0.00938 molar. It's gone pretty quickly. Now, the other concentration that we wanted was the concentration of bromide after 1 minute if you start with 1 molar. It's a bimolecular reaction. Every time a methyl iodide reacts, a bromide has to react as well. You could go through and solve the same math. The same math is going to get you to the same place. But since this is a bimolecular reaction, the concentration of the bromide left after 60 seconds, because we both started with 1 molar of each, is equal to the same amount. Alright, last but certainly not least is the stuff that's a little bit tricky. We're looking for, is it a plausible reaction? So we have a 2-step proposed mechanism. We know what the observed experimental rate is equal to. The experimental rate law is methyl iodide to the first power, bromide ion to the first power. So we need to figure out if this proposed mechanism is consistent with all of this data. So the first thing we have to do is make sure that this adds up to equal the balanced chemical equation. We have an intermediate. The intermediate is this weird CH3 positively charged species. It is formed in the first step and it gets consumed in the second step. So that's the only thing that cancels out. So the sum of these steps, methyl iodide plus bromide, yields bromomethane plus iodide. So check. Our first criteria to determine if the proposed mechanism is plausible is met. Now, the second thing we have to do is determine if the rate constant for the slow step is equal to the experimentally observed rate constant. And this is where it gets tricky, because we have that fast equilibrium. So the rate law for the slow step. So the rate law of the slow step is that it is equal to the rate constant times the concentration of this weird CH3 plus cation times the concentration of the bromide. That CH3 positively charged cation is an intermediate and it cannot appear in the rate law. So we've got to do more work. We've got to get rid of that plus CH3. So, when you have an equilibrium, you have the rate of the forward reaction. That's going to be equal to the rate constant for the forward reaction times methyl iodide to the first power. It's an elementary step, so the order of the reaction is based on the coefficients. The rate of the reverse reaction is equal to the rate constant of the reverse reaction times iodide times that weird CH3 cation. because it's an equilibrium, the rate of the forward is equal to the rate of the reverse. So we can set them equal to each other. Kf times methyl iodide is equal to Kr times iodide times methyl cation. We are trying to solve for the concentration of the methyl cation so that we can plug it in. So, here we go. We're going to divide both sides by Kr times iodide. So that means that Kf times methyl iodide divided by Kr times iodide equals methyl cation. We're going to take all of this and plug it into this rate law. We got to get rid of that concentration of the intermediate. So that means the rate of the slow step equals K times Kf divided by Kr times CH3I divided by I minus times Br minus. We can take all those values for the rate constant and plug them in and say that they're just equal to K observed times methyl iodide to the first power times bromide to the first power divided by iodide. This in no way, shape, or form is the same as the rate constant methyl iodide to the first, bromide to the first that we figured out in the very first one. This is the observed rate law. This is what we would get from the proposed mechanism. So, is this a plausible mechanism? No.